Cartoon lecture 36 infinite sequential series, and this is representations of functions as power series. So the first power series. In fact, a geometric series, if we usually use R for that, but if we use X, that's a power series. When the sum of a geometric sequence, say, geometric series. Let's look at this. So let's look at this then. Sigma, say x to the power n, and n starting at 0 to infinity. So that's 1 plus x squared. And what is this? This is a geometric series where a equals 1 and r equals x. So we know that if absolute value of r, which is x, is less than 1, then it converges to a over 1 minus r, which is 1 over 1 minus x. Okay, so this guy here, this interesting is a power series, in fact, converges to an amazingly nice function, 1 over 1 minus x. So let me write this here. Well, let me erase this thing and say that this guy here, in fact, using ideas from geometric series, we found that this is sigma xn is a function for x less than 1 as x less than 1. So it is fx, and we found that it is in fact 1 over 1 minus x. So 1 over 1 minus x has this power series representation xn. So that's what it says, representations of functions as power series. So I have represented this domain is in fact minus 1 and 1. Domain is this, right? X between negative 1 and 1. X is between negative 1 and 1. You can check the endpoints and you will see it is not convergent for the endpoints. At 1 it is 1, 1, 1, 1, 1, 1, divergent. At negative 1 it is minus 1, plus 1, minus 1, plus 1, does not exist. So it is not convergent at the two ends. So that's it. I didn't do that analysis, but you see that this is in fact the case. So the first function that we have found, and we have learned an explicit formula for this function. An explicit formula. This function 1 over 1 minus x is defined for every x except 1, right? But it can be represented as the power series if x is between negative 1 and 1. So let me draw some picture for you. Let's push that. So let see, I know I have enough space here. So what is this function? What does it look like? Fx is 1 over 1 minus x. We know from, say, elementary algebra that it has a vertical asymptote at 1. Okay? And what is the y-intercept? Y-intercept is x equals 0 will give me 1, so it goes through this point, right? So it is like this, and also as x goes to infinity and minus infinity, at infinity it is negative 0, say, so it's below 0. And at positive, plus at negative infinity it is above 0, so it looks like this. 1, and then it goes like this. Now, this analysis is telling me that 1 over 1 minus x has a power series representation of the form sigma x to the power n starting at 0 going to infinity when x is in this interval. When x is in this interval, not outside that. So what is this interval? This is point 1 and the negative 1 is here. So over this interesting interval, which is simply this much of the function, and it doesn't include this point, so the function, this guy here, that's the graph. The function over this interval, which has this graph, has a power series representation, not outside. So that's interesting that part of this, how should I say that? Over certain interval, you can write this function as a power series, not outside this interval. So outside this interval, we cannot do that. But you can, we might say, okay, what the heck? Why should we just restrict this function and say, okay, this function is just good in terms of power series only over this interval? That's enough. We will see. That's enough for so many things. In fact, this amazingly nice and simple function can give us lots and lots of other things. So, let's see what we can extract from this. Now, if let's say there are some facts here. Facts 1, if fx is represented by a power series on, say, A and B, then it can be differentiated on AB, and we have, so if fx is, say, sigma cn xn, then f prime x is simply sigma is the Cn states, and I have n x n minus 1. Now it depends, I'm not going to write n here, it depends on where n starts. So when you differentiate, then you should be careful when n starts. So because if I write n equals 0, I will get x to the power negative 1. That's not the power series. So I have to start at 1. Okay, now, so that depends on the situation. So I can differentiate this thing, and on this interval, I can differentiate the power series, and the derivative of this function, in fact, has a power series expansion over the same interval. And when we find this, the derivative, we again check the endpoint and see maybe the endpoints also are included in this. So, and also number 2 is something similar, and so 2, if fx is represented by a power series on AB, then it can be integrated on AB. Now, when I say integrated, I mean what's that? Definite integral, which you can give endpoints, or antiderivative. So antiderivative. So if I have fx is like this, again, n from 0 to infinity, Cn xn, then the integral fx dx is like this again. So it is sigma Cn xn dx. Okay. Cn xn dx, in fact the Cn comes out and you have a nice formula over, again, AB. Now, when you find the integral, you should write a constant here. So, if it is definite integral, then you don't need a constant. Indefinite integral or antiderivative, you need a constant here. So, it's amazing. These two are telling me that by differentiating or integrating the function over that interval of convergence, the open interval of convergence without the endpoints, we can come up with other functions. And those functions are the new functions. In fact, we have found other power series expansions for certain interesting functions. And you will see two of the most interesting and important functions, they come out of this idea, or these two ideas. So let me try this on the first function that we found by inspection. We found a power series form. So the first function, let me write it here, like the mother function here. So the first function is 1 over 1 minus x. It has power series expansion, x from 0 to infinity on a negative 1 and 1, okay? Not outside this. Now, example now, well, let's find the derivative, d dx of 1 over 1 minus x. So this will give me sigma, and from, let's say, 1 to infinity, remember I need that, d dx of xn. Now, what is on this side? What is d dx of this? This is, in fact, let me write it here, then I will erase it. That's 1 minus x to the power negative 1. d dx will be minus 1 times minus 1 times 1 minus x to the power negative 2, right? So then 1 minus 1 comes here. The derivative of this, in fact, is minus 1. So I will get 1 over 1 minus x squared. This is, in fact, sigma n from 1 to infinity. That is nx n minus 1. Nx n minus 1. So this function 1 over 1 minus x squared has this Taylor expansion. So power series expansion, and the domain is again, domain is minus 1 and 1. You can check the endpoints, not convergent at the endpoints. In fact, when you find derivatives, you will see that it's not convergent at the endpoints. This one. it's integral. When you integrate, that n comes in the denominator, right? So when you integrate, you might change the convergence. So you might add one of the endpoints to this interval of convergence, and we will see that. Okay. Now, this guy here, but I can write, instead of x, I can write minus x, right? If x is in this domain, minus x is also in this domain, right? If x is, say, minus 1/2, minus x is 1/2. That is also in this domain. Now, why does this happen? Number 2, since x in -1 and 1 implies minus x in -1 and 1, I can replace x with minus x, right? Replacing, we have, so if I replace that, 1/1 minus x, this should have the same interval of convergence, and I will get -1 to power n xn, because that's -1 to power n. -1 to power n is -1 to power n xn. So let's write this one. What is this? 1 plus x, right? That's 1 plus x. And so let's write this here. The second one that we found. In fact, that wasn't the second one, it was the third one. So let's write it as the second one here, then the third one was that 1 plus x is sigma. So that is alternating. This is alternating. But still it is not convergent at the endpoints. So the end, this doesn't change. This doesn't change. Now, if x or minus x is between -1 and 1, what happens to x squared? What if I write x squared here? Well, let me stick with this one first. I'm not writing, the derivative was there, so let's look at this thing and see if I can say something. So this is again when x is between -1 and 1. Don't say it wasn't minus x. Yeah, I know. Minus x between -1 and 1 implies that x is between -1 and 1. Because multiplied by -1, everything flips, and I will get x between -1 and 1. Right? So minus x also belongs to -1 and 1. The other way around, I mean, this doesn't make sense. So I'm just talking gibberish saying it. So if this, so if I multiply that's x bigger than -1, and let me see now. That is, yeah, that's correct. So, and the other one is minus x will be bigger than, so it will be less than 1. So what does this mean? X minus x is less than 1, be bigger than -1, so -1 minus x, 1. That's the same thing, right? So, yeah, I just wrote something that students usually write as a big mistake. So, anyway, now what happens if I write x squared here? So number 3 is this, 1/1 plus x squared. And let's write this. This will be x2n, right? And from 0 to infinity. And if I apply the the ratio test, I will end up with -1 and 1. So, in fact, let's use the ratio test and see what happens. Ratio test. this one. Limit as n goes to infinity. Remember, ratio test eliminates this, so I'm not going to write negative 1 to power n. X to power 2 times n plus 1 over x to power 2n. So that is limit as n goes to infinity. This is 2n plus 2, that is 2n, so it is simply limit of x squared. So limit of x squared is x squared. So x squared should be less than 1. This implies that x is between 1 and negative 1. Okay, so this is also on negative 1 and 1. Okay, so using the ratio test, so I did not use this idea again. I mean, the idea that I used to go from here to here. I just said, okay, this looks like this. It looks like this. In fact, not just looks like, because I just plug x squared here. So okay, if it applies to x, then it should apply to x squared. Then I said, okay, this is this power series, but what is the interval of convergence? So I used the ratio test, and I found that the interval of convergence is in fact the same thing. Remember, for the other cases, I had absolute value of x less than 1. X squared less than 1 is similar to absolute value of x. Why? Because if you take square root of this thing, you will get absolute value. Square root of this thing is also 1. So you will get absolute value of x less than 1. This it's equivalent to absolute value of x less than 1. Okay, so I'm almost ready to find those two functions that I promised, some important functions, and they come out of this using integrals. So number 4, integrating 1 over 1 minus x. So integral 1 minus x dx. And on this side, I said the integral applies, so I will get sigma n from 0 to infinity. There's a constant involved, but the constant is 0, so let me just write this x n dx. So what is on this side? This is minus ln of absolute value 1 minus x. Okay? On this side, I have sigma n from 0 to infinity, 1 over n plus 1, x n plus 1. Now, I can add a constant here, then you will see that the constant is 0. So, let's just look at this thing. So, usually we write this x n plus 1 on top, but let's do it like this, it's better. So, it tells me that ln of 1 minus x, in fact, it gives me an interesting and amazing formula to the 4. Number 4 gives me ln of 1 minus x is in fact minus sigma n from 0 to infinity of x n plus 1 over n plus 1. Okay? X n plus 1 over n plus 1, and let's find the interval of convergence. The interval of convergence includes this, but let's try. So limit as n goes to infinity of this guy here, x n plus 1 plus 1, so that's n plus 2, over n plus 2, x n plus 1 over n plus 1. So this is n plus 2, n plus 1, there is an absolute x coming out, and then I have limit of n plus 1 over n plus 2. So this is in fact absolute x. Absolute x less than 1 gives me x between 1 and negative 1. Endpoints. So let me erase this and find the endpoints. volume, endpoints. X equals -1 gives me, what is it? X equals -1 gives me sigma -1 to the power n plus 1, -1 to the power n plus 1 times 1 over n plus 1, and starting at 0 to infinity. And that's an alternating series, and 1 over n plus 1 is like 1 over n, so it is decreasing, and the limit is 0, so it is convergent by alternating series test. At x equals 1, we have sigma 1, oh, there's a negative, so it is -1 over n plus 1. Negative or positive, this is divergent. Divergent by P series test and comparison test and CT. Both comparison test and the P series test, they give me that this is in fact divergent. So what happens is that I can write this thing as I can say that Ln, and I can remove absolute value because x is between -1 and 1, and it can't be 1. It can be -1. -1 will give me 2, but anything above 1 will give me negative numbers. So I can remove that absolute value, and that is minus sigma, and from 0 to infinity of x n plus 1 over n plus 1. You can start at 1 and we write n here. Right? So if I start at 1, and domain or interval of convergence is in fact, it includes -1, doesn't include 1. So the integral in fact changed this. It added, and I said when you integrate, you are in fact adding, and most often you're adding one of the two endpoints. Now let's, so that is in fact, we will see that's in fact what the Taylor series or the Maclaurin series for Ln of 1 minus x, it can be used to find Ln. So if you ever wondered how your calculator finds Ln, well, I'm not saying your calculator that does this, no, but maybe like 30, 40 years ago it would do that. So it was installed, it was set in the calculator to find Ln using something like that. Well, you have to do some manipulations because we will see that this really is convergent here, but it doesn't converge so quickly. There are two things here. One, for what values of x does this converge, and how quickly does it converge? How many n's do I need to get a good approximation? Approximation is, say, the error less than 10 to the power minus 10, for example. So we will do the error analysis in that Taylor series section. So let me try another one. So let's take number 3. So it was number 1 I picked. Let's take number 3 and see what this one gives me. Okay, so let me, number 5 will be this. Number 5 is, let's take 1 over 1 plus x squared. What is the integral of this thing? All of it has a nice and famous integral. Integral 1 plus x squared dx. And that is what? Tan inverse of x, right? So, if I integrate this, I will get tan inverse of x is in fact sigma, and from 0 to infinity minus 1 to power n. What is that? 1 over 2n plus 1 x 2n plus 1, right? 1 over 2n plus 1 x 2n plus 1. And so I can just write it this way, n from 0 to infinity minus 1 to power n x 2n plus 1 over 2n plus 1. Okay. Since I started with this has an IC or interval of convergence for this one is negative 1 and 1. So this should include negative 1 and 1. Because as I said, in that interval of convergence, we can do antiderivative. Antiderivative has the antiderivative of this will be power series for antiderivative of this over that interval. So I have to check the endpoints. So you don't have to write the complete. So endpoints. What are the endpoints? So this includes negative 1 and 1. So endpoints x equals negative 1, and negative 1 will give me negative 1 to power 2n plus 1 times negative 1 to power n. What is it? Negative 1 to power n plus 1, n times negative 1 to power 2n plus 1, right? So that is negative 1 to power 3n plus 1. But the plus 1 definitely gives me just negative. So what is negative 1 to power 3n? Well, that's, I guess, so let's see. I have negative 1 to power 2n times negative 1 to power n times negative 1 to power 1. This is an even number. Negative 1 to any even is 1. And there's a negative 1 here, so this will give me, this one goes away because it's 1. So at this point I have a sigma negative 1 to power n plus 1, which is okay, n starting at 0 going to infinity, of 1 over 2n plus 1. Okay, so this is convergent by AST. Okay. Now what happens at x equals 1? X equals 1, I will get sigma, and from 0 to infinity, there's a negative 1 to power n already here, so negative 1 to power n of 1 over 2n plus 1, again convergent by alternating series test. That is amazing. So this one, in fact, is convergent at the two ends, and so it adds to that interval of convergence that comes from the original before integration. So I can just write this and say that with IC, with domain, which is in fact interval of convergence being minus 1 and 1. Okay. Okay, so that's in fact tan inverse. That is the how you can find tan inverse of anything. But be careful, you have to use radians here. Sorry, it will give you the value in radians, not degrees. So if I write, say, 1 here, for example, which is that endpoint, that should give me what? That should give me pi over 4, right? Tan inverse of 1 is pi over 4. So let's see what this gives me. So tan inverse of, so this is okay at 1, so I can tan inverse of 1 is pi over 4, I know that. Also, it equals what? Sigma minus 1 to the power n, 1 over 2n plus 1, and from 0 to infinity. So it is 0, and that is 1, in fact, minus 1 over 3 plus 1 over 5 minus 1 over 7 plus 1 over 9 minus blah blah blah. So this gives me that pi equals 4 times this. So pi is this. Pi is this. And you can just write a simple loop if you know how to program, and any programming language works, and you can find pi to any accuracy you want. But be careful, this one is not a good one because there are other approximations, but this one doesn't converge easily. It just goes up, down, and not up, down, but it's just so slow. You might end up adding billions of this, even more than that, I don't know. And still you are boom, slowly changing one bit of that. But that's one way to find pi. So, and there's also another thing you can tell from this that if you stop at some point, that is a good approximation for pi. But you can continue, and that adds or changes points, numbers after the decimal point. So that's one reason we can say that the pi is transcendental, because after the decimal point we have, say, it just continues, and those numbers after the decimal point are, they're not random, but you can, there's no, say, order to that, or no, what can I say, like a pattern to that. So that comes without any pattern. So that is one thing that comes out of the tan inverse. Let me see if I have nicer things here. Okay, so I guess that was what I had. And next time I will start the last thing in this chapter, maybe in this class. In fact, that is Taylor and Maclaurin series. So see you next time.